All right, Algebra 2. So now we're going to move on into the second part of section 3.2, which I've called 3.2b. And again, most other Algebra 2 textbooks would have broken this off into a second section. Our book decided to cram this in, so with everything else in 3.2. So we just finished solving systems algebraically. And the first method we did for that was something called substitution. And the key to all four of these problems we did was to try to isolate one of your two variables and then substitute that in for the other. Now, the concept of elimination works on something a little bit different, and I'd like to take just a minute to try to illustrate what it is that we're going to be doing within these problems. One little thing that most people don't know about equations, if you take a relatively simple, in fact, let's go with a very simple true equation, something like 2 plus 3 is equal to 5. Hopefully everybody's comfortable with that statement being true. If I were to take another equally true, simple mathematical addition equation underneath that, something like maybe 4 plus 6 is equal to 10, one of the things we can do here that's probably never occurred to you to try before is to add these two equations together vertically. And let's see what happens right now. So when I put the 2 and the 4 together, that adds up to a 6. I'm going to bring that plus sign straight down. The 3 plus 6 in the second column is going to give us a 9. I'll bring the equal sign straight down, and when I add up their sums, 5 and 10, that gets us 15. And now we had two statements right here that were both true. Now we've added them together to get a third statement. And what I want you to notice is that third statement is true as well. 6 plus 9 is equal to 15. So the quick lesson to learn here is that you can add two true equations together and get a third equation that is also true. If the first one is true and the second, when you add them together, the third one is going to be true as well. So we can use that to our advantage in certain systems of equations where, if we take a look at this example right here, where the equations are in the same form, that's the first thing. You'll notice these are both in standard form. And I want you to look very quickly here. This is our first example, so of course I chose one that was a little bit on the easy side for us here, guys. Something really nice happens that maybe you noticed right away. We have a negative 4y for the second term in the first equation and a positive 4y for the second term in the second equation. And I want you to think for just a second before we dive in, what's going to happen when I add these two equations the way that I added these two here vertically? Well, maybe you see it, maybe not. So let's go ahead and dive into it here, and we'll see what's going to happen. So we're going to add the first and second equations together vertically. In the first column, 5x plus 3x is going to get us 8x. And here's the really interesting part. The second terms, negative 4y and positive 4y, are opposites of one another. And what happens when you add together two opposites? That's right, they wipe out completely. They cancel each other out, and so the y's are gone. Or another way to put it, the y's are eliminated from this particular new equation that we just came up with. So I'll bring my equal sign straight down, and then I'll add the sums. The negative 1 plus 25 is going to get us a 24. So just like in that little example I did with you a second ago, we had two equations that, of course, we have to assume are true, and we add them together to get a third equation that's true as well. And the beauty of elimination now is that one of the two variables gets eliminated. So unlike equation 1 and equation 2, which were both two variable equations with an infinite number of solutions, we've added them together and eliminated the y's, and so equation 3 is just a one variable equation, which has only one solution. And we'll solve that by dividing both sides by 8, and lickety-split here, guys, we get x equals 3, and that is the first half of our solution to this system of equations. We now know the x value. Now, I like elimination better than substitution for the most part. I think it's less work. But one spot where it's probably more work is right here. When you got done with your first half of your solution in substitution, you took that back in to an isolated equation. Here it's just a little bit tougher. So you're going to have to decide, does equation 1 or equation 2 look like a better spot to put this value right here of x equals 3? I try to avoid negatives when I can, guys. So I'm going to move this right here into equation number 2, and I'll just push this off to the side here. So now effectively we are using substitution. I'm going to rewrite equation 2 with a 3, but instead of an x, we're going to put in this new value we just came up with for x, which is 3. So it's 3 times 3 plus 4y is equal to 25. And again now, this is a one variable equation. It shouldn't be hard to solve. The 3 times 3 is going to be 9 plus 4y equals 25. We're going to subtract that 9 from each side of the equation here, just like a good Algebra 1 student would do. We're going to get 4y is equal to, and the 25 minus 9 is 16. Last step here, guys, we're going to divide both sides by 4, and this should get us the second half of our solution, which is y equals 4. So now we're going to put all of that together into our final solution here. Our x-coordinate is 3, and our y-coordinate is 4. And what we have here, guys, let me box that up and put a little star by it there. That is the solution to our system of equations. That should be the only ordered pair that satisfies both equation 1 and equation 2. And again, if you really care about getting this right, let's go back and check it off to the side right here. So if I put in a 3 for x and a 4 for y, let's see what happens here. 5 times 3 is going to get me 15, and then minus 4 times 4, that's minus 16, and that should equal this value right here of negative 1. So look at that statement in red. Does 15 minus 16 equal negative 1? Check. Yes, it does. But we also have to satisfy equation number 2, so let's try that one. 3 times an x value of 3 is 9, and then plus, we've got 4 times a y value of 4 is going to be 16, and that should equal this sum right here of 25. So let's look at equation 2 now. Does 9 plus 16 equal 25? Check. So I checked both of the original equations, and this ordered pair satisfied them both. So I feel really confident now that we got the right answer here to this system of equations. It's the ordered pair 3, 4. Just so we haven't lost sight of what we're doing, equation number 1 here is a 2-variable equation. It has an infinite number of solutions. Equation 2, same deal. 2 variables and an infinite number of solutions. But there is only one solution that satisfies both equation 1 and equation 2 at the same time, and that's the ordered pair 3, 4. So that's the elimination method there, guys. And this one worked out pretty darn well and pretty quickly, but it worked out that way because I was nice and I gave you 2 y terms right off the bat that were already opposites of each other. Now that won't always happen, you guys, and so sometimes we have to work in order to make that happen. So let's go to example B right here, and let's take a look at what's happening here. Now at first glance, this looks a lot like the problem we just did. We have 2 equations, both written in standard form, and we're going to try to put them together in such a way that's going to get things to cancel. However, I don't want you guys to write down what I'm about to do. We didn't get as lucky here as we did with the last problem. If I were to add these up, which I certainly can do, I'd get an 11x, and then I would have a minus 4y is equal to 28. Now, this third equation that I've come up with is true. When I do eventually solve this system, I'd be able to plug that ordered pair back into this new equation 3 here, and it would work. But this doesn't accomplish what we needed it to accomplish. We did not get a third equation here that is only down to one variable. We didn't eliminate either the x's or the y's here, so there's really no point in adding them together. So we got to go back to the drawing board here, and we've got to do something a little bit different right here from what we did in example A. We have to decide right now whether it's going to be easier to eliminate the x's or the y's, and I'm going to show you how to make that decision right now. If I was looking at the x's, my coefficients are 5 and 6, and the least common multiple of 5 and 6, the smallest number they both go into, is 30. Now if I look at the y coefficients, I've got a 2 and a 6, and the least common multiple of 2 and 6 is 6. That's the smallest number they both go into. You want to choose the variable that has the lower least common multiple here. All right, there would be a few exceptions maybe to what I just said, but in most cases that's the case. I could do 30, but 6 is easier. That tells me that I'm going to eliminate the y's, although I still haven't told you how. Now, variables get eliminated when they have opposite coefficients. Like in the previous example, we had a coefficient of -4 and +4 on the y's, and so we put them together that way. Here, we want to eliminate the y's in this problem here by getting their coefficients to be opposites of one another. And that least common multiple we came up with a second ago was 6. This coefficient is already -6, which means I want this coefficient to become +6. And we do that with a little trick of multiplication. So you're going to ask yourself, what do I need to multiply this 2 by to make it become +6 so that it will cancel with this -6? And the answer to that is 3. So we're going to put a 3 right out here in front of the left side. And what I really should make you guys do is this. We're going to multiply the left side of the equation by 3 and multiply the right side by 3 at the same time. Now, this is probably the better way to write that, multiplying both sides of the equation by 3. But I'm going to let you guys get away with some bad notation right here. What we can do, just because it's informal here, guys, is put a 3 here and then put parentheses around the entire equation. Now, we're going to distribute that 3 to all 3 terms. And what I'm about to do is bad mathematical form. You never distribute over an equal sign, but again, really, there should be a times 3 here, and that's the multiplication you would do there. So we're gonna get away with that. I think we'll be all right with that. So what we're gonna do then, guys, let me pick it up down here. I'm gonna rewrite equation 1 down here on the bottom, distributing that 3. 3 times 5x is 15x, and then a plus 3 times 2y is 6y equals, and 3 times -14 is a -42. The second equation, we're just going to rewrite the way it was. 6x minus 6y is equal to +42. And now we have the 2 opposite coefficients that we were looking for, so now we're ready to go ahead and add these 2 equations together. 15x plus 6x is going to get us 21x. The y's cancel out, the y's are eliminated, and now this won't happen very often. This is kind of a coincidence right here. When we go to add together our constants, -42 plus 42, they cancel out as well because they are opposites, and we end up with a 0. A lot of people stop working at this point. They just say, wait a minute, everything else is gone, so I'm done. And then they don't know where to go next. Guys, this is really important. The equal sign never goes away. An equation never stops being an equation. And if you have an equation, you have to have something on the left, which we do, 21x, but you have to have something on the right. And if everything cancels, that's what 0 is there for. For all the work the Romans did in their great civilization, they never understood the concept of a 0. That came later, and so we put that there. Now, it's funny how often people totally abandon everything they know to do in a case like this just because they get scared of the number 0. It doesn't really matter what that number on the right is. You always do the same thing. We've got a 21x on the left side. I need to get rid of the 21. So I divide the left by 21, and I divide the right by 21. And these 21s cancel, and that leaves us with our x solution here. 0 divided by 21 is 0. Don't panic. There's no need to freak out and all of a sudden stop doing what you normally do just because a 0 popped up. There it is, everybody. That's the first half. The first half of our solution. And now that we've got x, we're going to go back to one of the 2 original equations to figure out what y is. And again, I said that I usually like to avoid negatives, so I'm going to go back to equation number 1 here, although you certainly could do this with equation 2, and it would work as well. That's going to be a 5 times our x value, which is 0, plus 2y is equal to -14. The 5 times 0 just wipes out, so we're left with a 2y is equal to a negative 14. And then, of course, we will divide both sides of this equation by 2 and get our y value here of our solution. Y is negative 7. So we know what x is, we know what y is. Let's put it all together into the ordered pair 0, comma, negative 7. And this should be the one and only ordered pair that works in both of the original two statements. Let's double check that real quick. Again, you guys never have to do this, but the students that do, they get this stuff a little bit better than the people that don't, and they do better on test and quiz questions if you learn to test your answer. Let's go to equation number 1. 5 times an x value of 0 plus 2 times an x value of negative 7 should equal negative 14. Well, that's 0. That's negative 14 there equals negative 14. Check. It works in the first one. And let's go to equation 2. 6 times an x value of 0 minus 6 times a y value of negative 7 should equal positive 42. Well, again, that's 0. And then negative 6 times negative 7 is 42. Equals 42. Check. That one works as well. So now I feel really confident that this answer we came up with here, 0, negative 7, is the correct solution, the only solution to this system of equations. Okay, so example B was harder than example A, because in example A, you were given right here and right here two coefficients on the same variable that were already opposites of one another. And in example B, we were not given that. And so that means that we had to multiply the first equation by 3 in order to get those coefficients on y to be opposites of one another. Okay, so let's take a look at example C now. And this is kind of, sort of, a little bit, the same concept as what we did in B, although the plot thickens even more here. Okay, first glance, it's not our favorite kind of problem. We were not given opposite coefficients right off the bat. So now it's decision time. 4 and 3 have a lowest common multiple of 12. 6 and 7 have a least common multiple of 42. That's big and ugly. It would work, but nobody's going to enjoy that. We're going to go with the 12 right here. So here's what we need to do. We need to turn this 4x into a 12x. So ask yourself, what can I multiply by 4 to make it become 12? The answer to that is going to be 3. So I'm going to multiply the first equation here by 3, and then off to the side, let me switch colors here. Let's go ahead and distribute that 3 in there. 3 times 4x is going to be 12x, minus a 3 times 6 is going to be an 18y, equals, now I would think you guys would grab your calculators here, but let's see, 3 times 60 is 180, 3 times 6 is 18, that should be 198, if I'm not mistaken. Now look at what we accomplished here, guys. We got the x coefficient to be 12. We need to turn this one into what number? A lot of people get this one wrong. We need to turn that 3x on the bottom into a negative 12 so that it will cancel with the 12 right above it. So the question now is, what can I multiply by 3 to make it become negative 12? And the answer to that is negative 4. That's going to take a little bit of practice there, guys. A lot of people mistakenly put a positive 4 there, and then their x's don't cancel out. Okay, so let's distribute that negative 4 and see where that gets us. Negative 4 times 3x is negative 12x. A negative 4 times a negative 7y is plus 28y equals, oh boy, and a negative 4 times 72 is going to be a negative. Quick way to multiply by 4 in your head, guys. Double your number and then double it again. 72 doubled is 144. That doubled is going to be 288. Look at me go. Okay, did we accomplish what we needed here? Did we get two coefficients on the same variable here that are opposites of one another? Yes, we did. We got 12x and negative 12x. So now we're ready to add up these two equations and come up with our third statement. Here we go. Negative 12x plus 12x cancel each other out. The x's get eliminated. Now, the y's are left here. Negative 18y plus 28y is going to leave us with positive 10y. And this definitely could be worse, guys. A positive 198 and a minus 288 is going to leave us with a negative 90. So, we did what we needed to do. We eliminated one of the variables, and now we're down to a third equation right here. That's a one-variable statement. We can solve this. We can divide both sides here by 10. Okay, lickety split, and we're going to get y is equal to negative 9. So I'm going to circle that. That's the first half of our solution. Now at this point here, guys, we need to figure out what x is, and you actually have 4 different choices for where you could put this y value. You could put it right here into equation 1, right here into equation 2. You actually could, if you wanted, put it there in equation 3, or right here in equation 4. Any of those 4 should work, although these would really be a bad idea right here. All we did is we scaled up equation 1 and 2, so it would work, but you'd be dealing with much larger numbers than if you did equation 1 or equation 2. Both of these look pretty much the same to me. I think I'm going to go into equation 2 here, everybody, and let's see what that's going to look like. So rewriting equation 2, this is going to be 3, I don't know what x is yet, minus 7 times a y value of negative 9, and that should equal 72. It's a one-variable equation, so let's solve that for x. We're going to get 3x. A negative times a negative is a positive 63. That equals 72. So we'll subtract the 63 from each side here. Okay, those are gone. And we're going to get 3x is equal to 9. We'll divide both sides here by 3, and we'll get x is equal to 3. And that looks like our x value. So putting it all together here, guys, hey, one mistake that I see people make is they'll write the answer as this. And the reason they'll do that is they'll think, well, I found the negative 9 first, so that's the first number I write. Then I found the 3 second. That's the second number that I write. Hopefully you guys realize why that's wrong. It does not matter what order you find your values in. Your x-coordinate always comes first, and in this case that's 3. The y-coordinate always comes second, which here is negative 9. So I believe that's our solution to our system. Let's double check that one and see if it works. Back into equation 1. 4, I'll do this in my head, guys. This 4 times our 3 value is going to be 12. Then I've got a minus 6 times a minus 9. That's going to be plus 54. That should equal 66. Check. Yes, it does. Into the second equation, 3 times 3 is 9, and then a minus 7 times negative 9 is a plus 63. That should equal 72. Does it? Check. So I feel really good about that. That's our solution here to example C, the ordered pair 3, negative 9. So that example is one of the tougher ones that's out there. That's where you have to multiply both equations by a number in order to scale it up to get opposite coefficients. And I've only got one more example for you guys here. And let's take a look at what's happening here in D. Okay, we did not get super lucky here just yet. We did not get coefficients that were opposites of each other at the beginning of this problem. So, kind of like example B, I think, we're going to have to find out which one to multiply by here and by what, and maybe both, in order to get things to cancel out. So, let's take a look at our coefficients. 7 and 21, the smallest number they both go into is 21. Here, we've got a 1 and a 3. You can ignore the negatives right here. The smallest number they both go into is 3. 3 is a lot smaller than 21, so I'm going to work on the y's here. So, if we already have a coefficient here of negative 3, we want this coefficient here on this y to turn into positive 3 so that they'll cancel. So what do I have to multiply by this coefficient of negative 1 to make it become positive 3? That's going to be a negative 3 multiplied by the first equation. So let me draw an arrow over here, and I think I'm going to have to copy the second one as well. Let's distribute that negative 3. We're going to have a negative 21x, and then a plus 3y is equal to negative 36. Now I'm just going to recopy the second equation with no changes. 21x minus 3y is equal to positive 36. We're going to draw a line underneath, and we're going to add these two equations together, and something weird is about to happen. Our plan here was to eliminate the y's, and sure enough, 3y and negative 3y cancel each other out. That's exactly what we thought would occur. But now something different happens than what we've seen before. I was not planning to eliminate the x's, but if you take a look at what we have here, negative 21x plus positive 21x, those are opposites as well. They cancel each other out. And so back to what I said earlier, an equation never goes away. If an equal sign was there at the beginning, it's there at the end. And there's got to be an expression on the left and an expression on the right. Now on the left, all of our terms have canceled out, so you now have a 0 over here on the left-hand side. And on the right side, negative 36 plus 36, those are opposites as well. You've got to have something on the right side that is a 0 also. So this is a little bit strange here, guys. What happened here for the first time in 4 examples, all of our variables dropped out, and we were left then with a statement 0 equals 0. So you've got to ask yourself one quick question now. If there's no variables, is this statement true or is it false? It's one or the other. Well, 0 does equal 0, so this is a true statement. And we haven't talked too much about this yet. When all your variables drop out and you're left with a true statement, this is when we are going to write IMS for our solution. And if you think back to your notes from the previous section, what that stands for, guys, and I'm okay with you abbreviating it, but it stands for infinitely many solutions. That is what happens right here in this particular problem. So in most of the cases, in fact, in all of the 3 examples that we've done so far in this section, there was just one solution. But what happened in example D? We ended up with a true statement and therefore infinitely many solutions. What this really means, you guys, is that if we were graphing these 2 lines, which is not how we're doing it, we'd come up with the first line that would look, I don't know, I'm just guessing right here. The first line would have looked something like that. And when we went to graph the second line, it would have had the exact same y-intercept and the exact same slope as the first line. So we end up drawing the same line twice. And back in 3.1, that's when we introduced this concept. There's an infinite number of points of intersection here, and that's why our answer here is infinitely many solutions. So just to put a little cap on everything here, guys, to wrap this up, if all your variables drop out and you end up with a true statement, like for example, if you get 8 equals 8, okay, here's the way your progression of thought should work there. That is a true statement. And when you come up with a true statement, your answer is IMS, infinitely many solutions. So that's one case. The other possibility, though, when all of your variables drop out, is that you end up with a false statement, like 5 equals 11. And if that happens, you want to make at least a mental note and probably write down that that statement is false. And when you end up with a false statement, that is when you have no solution to your system of equations. Okay, so those are the 2 special cases that happens. Now, the majority of the time, you don't end up with a statement that's true or false. You end up with a variable in there, like 3y is equal to negative 18, and then you solve that and you get y equals negative 6, and in that case, there is one solution to your system of equations, and that's the one that happens most frequently. These ones up here, guys, are the 2 kind of exceptions to what we normally think we're going to see. So just be aware, everybody, these are the 3 things that can happen, either through substitution or elimination. And technically they happen in graphing as well. These are the 3 things that can happen when you're solving a system. All right, guys, that is a wrap on a very long section of notes on 3.2, which we broke up into 2 videos. Hopefully that makes some sense for you and it wasn't too hard to digest in 2 different pieces. So you guys give that homework a try. Let me know how it goes, and good luck, everybody.